In this video, we are going to learn about infinite limits at infinity. So there are two different type of things. So infinite limits, that means we are talking about y values. At infinity, we are going to talk about x values. So, so these are the kind of limits we can talk about in this one. So let's say limit when x goes to one of those infinities. It can be one of those infinities plus or minus infinity. So you have a function and the output is also plus or minus infinity, so one of those infinities. There are four different cases here. So if you look at the graphs, so this is the first one, so you can see things like this. So you have the function, so x gonna go to positive, x gonna go to infinity, and then y also go to infinity, so like that. So x goes to infinity, y goes to infinity. And the second one is uh, x goes to infinity, y goes to negative infinity, going like that. And then we have the third case, x goes to negative infinity, y goes to positive, like that. So when x goes to negative infinity, y goes to positive infinity. And the fourth case is when x goes to negative infinity, y goes to negative infinity. So those are the four different cases that can happen when under this situation. So, so let's look at several examples here. So you can see that so x get infinitely large, and then also y gets infinitely large. So let's look at special cases. So the one interesting one to start with is would be this one. So what about let's say find the limit um, when x goes to infinity, x cube. So it's maybe a good idea to like look at the graph. It will be very clear to get it. So you know that the graph of x cube is like that, passed into 0, passed to 0. So you can see clearly when x goes to positive infinity, y also goes to positive infinity. So, and also it's just x, so you can see when x increases, x cube increases, so it is positive infinity. And then what happens if limit when x goes to negative infinity, x cube? And you can see again it's a cube, it's an odd number. So that means if you raise a negative number to odd power, it is negative. So that means the answer is negative infinity. And it's also very clear from the graph when x goes to negative infinity, y goes to negative infinity. So looking at the graph may be like a kind of quick way to get this information. Okay, so in general, let's look at this one. Um, so for a polynomial, so if you have a polynomial, so polynomial are the like kind of the best class for these kind of functions, because you can see with polynomial this always happen, because you know like each polynomial, if you look at the end behavior of the polynomial, so what happen is if it has a even degree, it's going to go to one direction, so it's going to go like that. That's for the even degree. Positive leading coefficient, even degree, negative leading coefficients. So I'm going to go like that. So you can see they are going to infinities. And then so this is the so axn, n is even, so go to the same direction. Here we have a negative, here we have a positive, and then odd degree. If you have odd degree, what happen is gonna go like that, two different directions. So this is a positive, and then this is a negative. So gonna go like that. So this is for a negative. So what happened here is a x n. Now n is a odd number. N is odd number. Okay. Even the line follow under this category. Okay, and you can see that all of them are um, infinite limits at infinity. So this is like a really good example for this case. So go to negative infinity. Here it is infinity, negative infinity, infinity, negative infinity. Okay, that's for polynomial. So polynomial uh, have infinite limits at infinity. And in like special example would be this one. So we can say example, find the limit of find the limit. We can say x goes to negative infinity of fx, where you can say fx equal 7x cubed minus 5x squared plus 100 or something like that. So and in this case you can see that when x goes to infinity, when x goes to infinity, when x goes to actually negative infinity, fx, you can see that it is 7x cubed. So that is the dominating term, and thus carries the shape of the graph, shape of the function. So that means 7 is a number. This is positive number. So x cubed, that means it's going to go to like this. Since the graph is like that. So that means the answer is positive infinity. Okay, so let's look at several other examples. Like how about this one? A rational function. So a rational function. So when you have a rational function, so limit x goes to infinity, x squared plus x over 3 minus x. So we use the same logic or same argument that we used earlier in the main lecture. So what we can do is we can divide by the largest x power in the denominator. So which is x, so we can divide all the terms by x. So once you do that, you get 1x here. If you divide by the x, you get 1 here. And then 3 divided by x, and then minus 1. What we did, we divide each term by the largest power of the denominator. So once you do that, and then you can see when x goes to infinity, this term goes to 0. So that means the denominator goes to negative 1. That's what happens. So the denominator gets closer and closer to negative 1 because of this x term which goes to infinity, and because of the negative sign, this whole thing goes to infinity, but the negative sign, so negative infinity. So it is negative infinity. So that's the infinite limit of this one. So as a good exercise, why don't you try this one? So let's say limit x goes to positive infinity for x cubed minus x plus 5 divided by 5x squared plus 8. So this is like not a difficult problem, so you can try it. So this happens when the degree of the numerator is bigger than the degree of the denominator. So this happen when so infinities happen when the degree of the numerator is bigger than the degree of the denominator. Because you know that for rational functions there's like a special criteria that we normally do in pre-calculus. So the criteria is we're going to break this into four different types depending on the degree, and then we can categorize these rational functions as four different type of behavior when x goes to infinity. And if you are not familiar with that idea, because here what we do, we just find the limit, that's it. The limit tells you everything. But what happened in a pre-calculus class, we just use the degree method, and then looking at the degree, you can tell what happened, whether they get like a 0 asymptote some fine asymptote, no asymptote, or oblique asymptote. So if you are not familiar with that, you can find the link in the description for how to find the limits, or how to find the asymptotes for horizontal asymptote for rational functions, horizontal asymptote for rational functions, and you can find the link in the description. Okay, so let's look at two other interesting examples. How about this one? So let's say I'll find the limit when x goes to infinity, x squared minus x. You see that you need a parenthesis around, otherwise it doesn't make any sense. Okay, so what happened in this case when x goes to infinity, and you can see that x squared goes to infinity, x also goes to infinity. So it's like x minus x, infinity minus infinity. Infinity minus infinity is a doesn't define. So there's no meaning of this. No meaning. So what we normally call indefinite form. Indefinite. So one of the indefinite forms. So that means we need to use some other trick. So we can just subtract infinity and say 0. It's not 0. So it's not equal to 0. It's not equal to 0. So what we can do is we can use the argument that we use at the beginning of this lecture in the lecture 9, and you can see you can disregard this term, because the reason is x squared grow much faster than x, since because x goes to infinity, so x squared grow much faster than x. So that means compared to x squared, x is negligible. So if once you neglect, you can see that you get x squared when x goes to infinity, x goes to infinity. So answer is infinity. So that's one way to look at it. Just neglect the small order terms. The other way is you can use simple factoring argument. So let's see this argument. So that's one way to do it. Just look at only the higher order terms. The second method is factor. So if you factor, see what happens. So the factors are, one is x, the other one is x minus 1. Now you can see that when x goes to infinity, x goes to infinity, x minus 1 also goes to infinity. So infinity times infinity is infinity. So that makes sense. So it is infinity. So that's the other way to do it. Just factor and then look at the factors and write it like that. So infinity times infinity is infinity. So that's one way. The other method is you can just neglect the smaller order terms and look at only the larger terms. So that's one way to get the answer. So there are more indeterminate forms, like for example, if you have a term like 0 to 0 times infinity, at the limit, this is also another indefinite form. If you multiply by 0 itself, then it is 0, but that's not the case. We are talking about limits. When we talk about limits, this is indefinite. We don't know the exact meaning of this. We're gonna do these things later when we talk about L'Hopital's rule, but right now you can like use like algebraic arguments for that. Okay, and then let's do one more problem like this. So let's say find the limit of we can say when x goes to infinity, sin x. So what happened at the infinity? And you can see if you look at the graph of sine, sine graph fluctuate indefinitely. So it's going to go like that. So and passing through 0. So that's the sine graph, and then you can see that it doesn't get close to any particular value. So this is a sine graph. You can see that it's just fluctuates. So that means this limit does not exist. So the infinite limit doesn't exist. So the same thing happened with all of those trigonometric functions, main functions. But for tan inverse, I hope remember if you look at the graph, it is it's finite. It's a finite value. So for example, if you do the same thing with tan inverse, so x goes to infinity, tan inverse x, so which is pi over 2, because this part is coming from the graph. So we did this multiple times, and if you do not remember, that's the graph of tan inverse. This is gonna go like this. Okay, so this graph of tan inverse. Okay, so this is the idea about infinite limits at infinity. Before we finish the discussion, let's look at this interesting example. So find the limit when x goes to infinity and the asymptotes, if any. So clearly we can see that the denominator can never be 0. So that means there are no vertical asymptotes. So no vertical asymptotes. About the horizontal asymptote, what we normally do is we take the limit and see whether you get a finite value. If you get a finite value, there is a horizontal asymptote, and then clearly we can see that in this problem, a limit when x goes to infinity, y is, if you divide by x squared term, which is the largest term, you're going to get 12x plus 9 plus 5 over x squared. That's what happened in the numerator. To the denominator, you get 3 plus 4 over x squared. And then you can see that when x goes to infinity, this goes to 0 and that one goes to 0 as um, x goes to infinity. Actually, I forgot to write the limit. So what happens is when you look at the limit, so you can see the limit is, so the denominator is stuck at 3, but this part goes to infinity, so that means the limit is infinity. So it's an infinite limit. Infinite limit. So because of infinite limit, you can see that there are no horizontal asymptote. No horizontal asymptote, because you do not get a finite number. So the reason is this not finite. Not finite. But this one has an interesting um, asymptote, but those are what we normally call oblique asymptotes. You get an oblique asymptote. So how to get the oblique asymptote? So what we're gonna do is, so it's very clear what the oblique asymptote is, because if you look at this fraction, this can tell you what is the oblique asymptote. But let's see how we normally do a problem like that. So what we can do, we do just the lone division. So let's do that. So we have y equal 12x cubed plus 9x squared plus 5 divided by 3x squared plus 4. So if we do the lone division, we can write it like this. Don't forget to put zeros where they as placeholders, just to avoid confusion. So if you divide, what do you get? You get 4x here. So when you multiply, you get 12x cubed plus 0, and then plus 16x. So when you subtract them, so you can see the 12x squared term will cancel out. So you get 9x squared. When you subtract, you get negative 16x. And then you bring 5 down here. And then what you do, you're gonna, you see that 3x is missing. 3 is missing. So you get plus 3. So you get 9x squared plus 0. And then plus you get 12. Now you can subtract. So when you subtract, you can see you're going to get negative 16x minus 7. So that's the take, negative 16x, negative 7. Okay, so that's a fraction we get. And then we can write this one as a, in the standard form, like this. So we have this equals to the quotient, so which is 4x plus 3, and then you can see that in the remainder there's a negative sign, so you can pull the negative sign out and we can write this one as negative, and then 16x plus 7 divided by 3x squared plus 4. So we can write it in this form. Now as x goes to infinity, so you can see something interesting can happen when x goes to infinity. This term, because we have a larger denominator, so this term goes to 0. So what happened um, since this term goes to 0, you can see, so you're gonna get, so this whole fraction getting closer and closer to that one. So that means it's going to produce a what we call oblique asymptote. So that's oblique asymptote we get. So that means you can see we can write like this now. So limit as limit you can say x goes to infinity y which is equals to the limit when x goes to infinity 4x plus 3. You can see these both are infinity, but even though they are infinity, you can see the two expressions get close. So that means what happened is so we get y equal 4x plus 3 becomes an oblique asymptote. Oblique asymptote. So that's how you're gonna find oblique asymptote using calculus. So what happens is that fraction goes to 0, and then the expression y getting closer to the quotient part, which is 4x plus 3 in this case, and that's going to produce a oblique asymptote. So that's how you can use the calculus to find the oblique asymptote. And if you look at the graph of this function, this is what you get. So this is the graph of the function and the asymptote. The blue curve is the oblique asymptote, and you can see that it is getting closer and closer to the curve. Thank you.